today and to be able to talk a little about my work. So this work was made in collaboration with Claudio Gallegos. He is my former PhD student, and Professor Hernan Henriquez from Universidade de Santiago de Chile. So the goals of my talk, I will talk about this class of equations, that's the hybrid measure differential equations, and I will talk about some results concerning these types of equations. So the outline of my talk, I shared this in the following way. I will start talking about a little about these measure differential equations, and then I will talk about the relationship between these types of equations and the other types of equations, such as dynamic equation, time scales, impulsive differential equations. And then I will talk about some results that we got from this paper. And then I will talk about some open problems in this area. Here, about these connections between measure differential equations and other types of equations is to give some motivation to investigate measure differential equations. So I will talk that how we can encompass many different types of equations inside of these big sets. And then we will see that all the results that we prove for this class of equations, we can translate to other types of equations. So in order to start my talk, to talk about these types of equations, that's the measure differential equations, I will recall very fast about such a type of integration that we use here that's a more general than Lebesgue integration. So here we start in 1957 with Jaroslav Kurzweil, and he was very interested about to understand the Kapitsa pendulum problem. And in order to investigate this type of problem, Jaroslav Kurzweil needed to deal with highly oscillating functions. And for that, he needed to introduce a more general integral, that more general than Lebesgue integral, because he needed to integrate these highly oscillating functions. And in order to investigate the behavior of this pendulum, he proved some continuous dependence on parameter results, and then used these results to apply averaging methods to have some approach about the solutions, about the behavior of the solutions, and then to investigate it deeper about this type of pendulum. At the same time, but completely independent and investigating other types of problems, we have that Hauff-Henstock also introduced in the literature a new type of integral, more general than Lebesgue integral, but with a different concept, if you see, from the Jaroslav Kurzweil. But then later they found out that both were equivalent. And that's why this is called Kurzweil-Henstock integral or Henstock-Kurzweil integrals. And here it's only an example. If you have this type of function here, it's possible to calculate the derivative of this function that's given by this. And the derivative is not Lebesgue integrable. As you can see, that's very highly oscillating function, but it's Kurzweil-Henstock integrable and also Perron integrable, because Perron is also equivalent of as Kurzweil-Henstock integrals. So here we are interested about these types of integrals, that's the Henstock-Kurzweil or Kurzweil-Henstock integrals, because in our type of equations, we consider that the Stieltjes integrals that will appear in our equation will be in the sense of Henstock-Kurzweil-Stieltjes or Kurzweil-Henstock-Stieltjes integrals. And in order to introduce this notion, we started with the tag division. That's a very simple definition. So you have here some interval, compact interval, and a tag division is only to cover this interval with subintervals. So here we have these subintervals here, and in each subinterval we choose a tag. So here we have, this is a tag division of the interval AB. And here is the main difference of the definition of Kurzweil integral and other types of integrals. That's the gauge. So given a function that's only a positive function, this function is called a gauge. We have that a tagged division is delta fine whenever we have this inclusion here. So this will be very important here in the sense of this integral because we can calibrate and we can run away from the discontinuities or the bad behavior of our functions. And so here we have the definition of this Kurzweil integral. So we have that a function u is called Kurzweil integrable if we have this type of inequality here holds for all tagged division delta fine. And here, depending how you define your u, we can have the integral of Kurzweil-Henstock. That's a particular case of this more general Kurzweil integral here that I am presenting. And also, depending how you define your u, we can have the Kurzweil-Henstock-Stills integral. So if your u tau t is defined by f of tau and the g multiplied by g of t, we have that this is equivalent to have the Kurzweil-Henstock-Stills integrals. And in order to ensure that this integral is well defined, we have this Cousin lemma that ensures that given a gauge, there exists a tagged division delta fine of the interval AB. So with that, here I would like to introduce this type of integrals because we will see that when we deal with measured differential equations, we are dealing with an integral equations, a type of integral equations, and we will have a type of Stills integral in our right-hand side of our equation, and this integral will be in the sense of Kurzweil-Henstock-Stills integrals. So, but before to go to our problem of today, we will talk how it's so nice to deal with this type of measured differential equations because we can put inside of measured differential equations many different types of equations. So first, I will talk how to relate measured differential equations with dynamic equation timescales. And in order to be able to talk about it, since I'm not sure if everybody here in audience is familiar with dynamic equation timescales, I will give a very, very brief overview about these types of equations. So for that, we need to start with the theory of timescales. And it started in 1988 with Stephen Hilger in his PhD thesis. Here is Bernard Albach, his advisor. And Stephen Hilger, he would like to introduce such a type of theory that could unify continuous and discrete cases. And it motivated him to introduce these types of theory, that's the theory of timescales that unify continuous cases, discrete cases, and also the cases in between. So here we have the definition of a timescales. A timescale is a no-empty and closed subset of the real numbers. So we can have many, many examples. And for the discrete case, we have that Z is also, yes, a closed subset of the real numbers and is also timescales. And this is the type of the difference equations. And here, when we have the real numbers, we have that this is the differential equations, but we can also have much more complicated timescales, such as Cantor set, or for example, the union of closed intervals. And in that case, we can have the hybrid behaviors. Also, we can have a very special type of timescales that's called quantum scales. That's very important for quantum physics. And we can have much more examples of timescales. And here, the only definition is that it's a no-empty and closed subset of the real numbers. And because of this unification that timescales brings, that's why this theory is called summatation of many mathematicians. So we can unify continuous and discrete cases. Also, we can unify ordered cases depending on the chosen timescales. And also we can have some applications for some models, especially when we have the hybrid behavior, because sometimes we have that some phenomena happens like continuous and then discrete and then continuous and so on. So when we have this type of behavior, we have the timescales fits very well to describe this model. So now let's see how we can relate measured differential equations and dynamic equation time scales. So one thing that we needed to start to think when we try to do such a connection is that measured differential equations is defined in the all real line. So we have the continuous case. But when you deal with dynamic equation time scales, we can have some holes in our domain. For example, when you deal with the integers number sets, we have some holes in between some points. And these holes, we need to fulfill them in order to establish this bridge between these two types of equations. So in order to do that, we need to define some operators that can extend our time scales and the definition of our functions for these holes that we have when we deal with time scales. So here we define this operator that is called a star operator, and we define this T star as the infimum of all the points in the time scales such that it's bigger or equal T. And also here we define the extension of the time scales, exactly to fulfill all these holes that could appear in our time scales, and it does not appear when you deal with measured differential equations. So here it's given by minus infinity until the supremo of the time scales, if we have the supremo is finite, and here is the real line if we have that the supremo is infinite, the supremo of the time scales. And using this operator, this star operator, we can define the extension of our function f. So here we have a function that's defined on the time scales, taking values here is Rn, but we can have also any Banach space that we want. And here we would like to extend this function because here it's defined on the time scales, but we want to define this for the extension of the time scales. And that's why we use this star operator. So here f star of t, it's equal ft star for all t in the extension of the time scales. So in order to visualize that, to illustrate this definition, we can have here an example. So here we have this function that's defined only in the time scale. So here the time scales is the union of these three intervals here. And I want to define an extension of this function that I will call f star t using the definition before. And what we have is that if I take some point here, it will be equal ft star, but t star, it will be exactly the infimum of all the points in the time scale such that it's bigger or equal this point, and it will be exactly c. And that's why we have this quantity here. So using that, we can fulfill all these holes that appears in our time scales. So we have this extension of our function f. And now using this extension, we are able to relate some relations between the delta integrals in the sense of time scales and a type of a Still's integrals. So here we have this delta integral in the sense of Kurzweil-Hansdorff, but here for the time scales. And we have that this is the F1, that's the integral in the sense of time scales. And here is F2, that is the integral in the sense of Still's integral, both in the sense of Kurzweil-Hansdorff. So Kurzweil-Hansdorff delta integrals and Kurzweil-Hansdorff Still's integrals. And if we define our G as the S star operator, so we have here that F2 will be equal F1 star. So we have this relation between the Still's integrals and delta integrals. Of course, here we take in a more general sense, that's the Kurzweil-Hansdorff integrals, but we can also have this relation in other senses of integrals, such as Lebesgue or Riemann integrals. So using this relation, we can relate the dynamic equation time scales with measured differential equations. So if I have that X is a solution of the dynamic equation time scales given by this here, then we have that X star is a solution of the measured differential equation given by this, where G is exactly S star. So we have this relation. And also, if I have that Y is a solution here, Y should have the form X X star, where X is a solution of this problem here. So we can have a relation between these two. So if we have a result here, we can translate the result here. So that's why it's nice to deal with this type of measure differential equations, because we can prove the result for that, and we can have as a consequence a result for dynamic equation time scales, which means that we can have the results for difference equations, hybrid equations, and so on. So this is one of the motivations to deal with the measure differential equations. And here I will bring another motivation that's that we can relate the measure differential equations with impulsive measure differential equations. So also we can have the impulsive behavior inside of these measure differential equations. So in order to do that, we need to consider what's the measure functional differential equations with impulses, and it's given by this here. So here we have this equality for all U and V in the intervals, except in the moments of impulses. Here we are considering that the moments of impulses are like prefixed, so we know where we have the moments of impulses and the increasing sequence here of the moments of impulses. So here we have it has this type of behavior outside of the impulses, and here is the jumps in the moments of impulses. So here we have these jumps here. And here is our initial condition. So here only to mention, I consider here with delay, but we do not need to consider here with delay. So here it's more general, but we can think about it without delays, because we can also extend it for delay equations the same way as before. We can have that measure functional differential equations can have a relation between measure functional dynamic equation timescales, but we can also think here without delays, so we do not need to consider like that. So here we have this type of equation, and if we assume that G is a left continuous function, and more than that, G is continuous at the moments of impulses, we can here write this type of equations in an integral form given by this here. So if we assume that G is a continuous in the moments of impulses, so we will have that this Still's integral will also be continuous at the moments of impulses. And doing that, so we avoid that this type of integral jumps at the same time as the impulses operators, and then we can here write our solution in this way here, in this integral form. So we have this is our impulsive problem. And when we have that G is the identity, we have that this is the impulsive equation. So we can have a relation between measured differential equations and the impulsive differential equations. So we can have this bridge. So in order to have that, so here you describe how we can relate it. So we define our F tilde equal our function F for all the interval except in the moments of impulses, and this F tilde will be equal the impulses operators in the moments of impulses. And then I will define this G tilde equal G except by a constant, so will be equal GT for this T in the first interval, and then will be equal GT plus some constant in the other one, and so on until the last part. So using that, we have that if X is a solution of the measure differential equations with impulses given by these, then we have that X is also a solution of the measure differential equations with F tilde and G tilde that we defined before. And also we have the other way around. So if we have that X is a solution here, then X will be a solution here. So using that, we can see that the measure differential equations can also encompass this impulsive behavior. So it's also possible to have a relation between these two types of equations. And then here, if you prove a result for this type of equation, we can translate for these equations. So that's why it's nice to deal with the measure differential equations. So let's see now about our problem here, what we are interested to do. So we are interested about the hybrid measure differential equations that is given by this type of problem here. So here we have this type of Still's integrals that is in the sense of Kurzweil-Hansstock Still's integral. So we have a more general. And here, depending on our function g, we can have the behavior of our x and also depend on the behavior of our h. But here, for example, if g is discontinuous, so we can have that our solution is also discontinuous. So we can have here, using this type of equations, such a type of discontinuous solutions. And here we have this type of perturbation. And as we saw before, these types of equations, including measured differential equations, can encompass many types of equations. So here, we can have that this type of dynamic equation on time scales can be encompassed in this one here. So we have this one is more general, and we can translate all the results that we prove for this type here of equation. Also, impulsive equations of this type. So here we have this hybrid type, and here we have this can be written this way here, and also we have a relation between this and this one here, and then we can translate all the results from this to this one here. And also, more than that, I didn't bring it here, but it's also possible to extend all the results for measured for dynamic equation on time scales with impulses, because as we saw before, we could have like g here. We could have this relation with g and this and our hybrid measured differential equations. And with this g here, we can have a relation with delta integrals, as we saw before. And using that, we can have a relation between these types of equation and this one on time scales. So we can have all the relation between these types of equations, and then proving a result for this type of equation, we can translate these results for all these other types of equations. And that's why it's interesting. So let's see a little about the results that we've fought in this type of problem, in this type of work. So we started with some existence of solutions, but here we didn't only bring the usual ones. We tried to have a more general conditions concerning the existence of solutions. Also a little about the differentiability of solutions. It's very important to mention that, as we realize here, it's very complicated to ensure such a type of irregularity of our solutions, because our G here can be discontinuous, and also we don't know about this H. So that's why to investigate about the regularity here, it would be such a type of interesting in that sense that we maybe do not have the continuity of the solution or differentiability, and to see some cases where we can ensure the differentiability of solutions could be very important. And also, it's also important to mention that here we have the usual derivative, but sometimes we can have a more general derivative when we deal with this d that appears in our integral. And we can have that a type of derivative g that is the same way as we have the limit of, if you would like, that x prime of t, in the usual sense, we have it will be the limit when t go, x prime of t0 will be the limit when t goes to t0, xt minus xt0 divided by t minus t0. But when we deal with this g and we think about the derivative in the sense of this g, we can have that this quotient will be not below the identity, but g of t minus g of t0. And this, when we have that g is the identity, we have the usual one, but we can have a much more complications when we deal with different types of g. So it's still such a type of investigations that they are studying depending about the regularity of G, but it would be very interesting to think about this. But here we do not work with this type of derivatives because we are dealing with the integral form directly. So we have in this form. So we do not need to deal with this derivative of G prime. So here also we investigated about the existence of asymptotically omega periodic solutions, which means that these asymptotically omega periodic functions is that when you have the difference between such a function that is f of t plus omega minus f of t, this goes to 0 when t goes to plus infinity. But here we are interested about to think if there are the existence of such a type of asymptotically omega periodic solutions, asking such a type of conditions concerning our function f. So we could prove some results in that direction using fixed point theorem, so it was not so complicated. But it would be nice also to extend this type of results not only for periodic or periodicity, but also almost periodicity or almost automorphicity. So it's some open problem directions. But here, for this one here, we could prove the existence of these types of solutions. And also here, we proved some results concerning the continuous dependence on parameters, and this one I will talk more about, and about this type of results. So let's see about the continuous dependency results. So for that, we considering the following sequence of problems. So here we have these K problems. Also, we could consider here for the G. We didn't consider in this, but we could consider that, and it will also be possible to prove it. And considering that, and some conditions, of course, also some conditions concerning regularity in order to ensure that this problem has solutions. But I skipped this because I will not prove the existence results here, but we made that in the first part. So assuming the same types of conditions, we can ensure that this one here has solutions. And some more, if we have that this sequence goes to x0 when k goes to infinite, and also this one goes to here uniformly as k goes to infinite, and also this type here of convergence concerning our function f. And here we assume such a type of a boundness of this f for such a types of functions m, and assuming that, and assuming this type of inequality here, and also this quotient smaller than 1, we can ensure that there exists a subsequence xk that converges uniformly on J to a solution X of our problem. So we have that, we have the limiting problem, and we can find a sequence of a subsequence of solutions of our problem that converges uniformly for our problem, for the solution of our problem. And here it's very nice, this type of results, because especially because here we are dealing with measured equations. And if we considering like a GK here, it's also possible to extend if we assume that GK goes to G. And here, doing the relation between these types of equations and, for example, dynamic equation time scales, when we do some type of convergence like that, when we translate it for dynamic equation time scales, we can also have some relations between the time scales that converges. So the solutions of the dynamic equation time scales can also converge, and also we can see the convergence concerning the time scales. And we can have a lot of important applications in this sense. For example, we can investigate a type of time scales that when the time is belongs for example, 1 over k and zeta, and when k goes to infinity, we have that this time scales converge to the continuous case for the R. And in this case, we can have that the solution of our problem for the discrete converges for the continuous one. Of course, in considering appropriate topology and also appropriate conditions, we can ensure this type of convergence, and we can investigate our problem for the discrete case that's easier to like make some computations. And then using this type of convergence, we can infer some behavior of our solutions for the continuous case. So that's very nice to have these types of problems, because we can apply that for these types of results. Also here, using this continuous dependence on parameters that we have in this way, what also we can have is applications for averaging methods. So when we have a non-periodic averaging principles, we can prove it using continuous dependence on results like that. So using this type, we can also have such type of averaging here for these parts, depending how you define it. And then applying the continuous dependence results, we can prove the averaging methods for the non-periodic cases. So we can have a lot of applications from these types of results. And that's why we were so interested about these continuous dependence results. Here we proved this one, but we are trying to prove others type of results. For example, if we have this type of problem, so if we can ensure that, or not this exactly, but if we have the limiting problem, if we can ensure that we can construct a sequence of problems, that there is a sequence of solutions that converges for the limiting problem. So also the other way around, we are also trying to see if we can extend these types of results for that. And to prove it, we use here some basic tools that about such a type of convergence theorems, but here it's only important to mention that we are dealing with not continuous solutions, and that's why we have such a type of difficulties here, because we are dealing with regulated functions, and then we need to prove to use such a type of Arzelà-Squally theorems for regulated functions, and also equiregulated sets, and we needed to deal with that in order to prove our types of results. Also, we needed to use here to apply such a type of Grow inequality, but not the usual one, but for the Stieltjes integrals in this sense. So using that, we can prove the results for this type of problem. So we can prove these types of continuous dependence. Also, for example, for the other one that I mentioned, that if you have your limiting problem and you'd like to construct your sequence of problems, that we have the subsequence that converges for the limiting problem, we can also use here the Heller's choice theorems in order to have this type of convergence. So also it's possible in that way, and it's in that direction that we are working now in order to have this type of results. So here, that's what we made in that problem, in that work. And now I still have some time, and I would like to talk a little about some open and developing problems in the area. So here, one first question is about measure differential equations. We know that dynamic equation time scales is a special case of measure differential equations. However, there are some questions that always I hear a lot about this question, that is it possible to have the opposite way? For example, for any measure differential equation, we can have a dynamic equation time scales associated to that. And we don't know this question actually, if it's true or not. We know the other way around. For example, if we have a dynamic equation time scales, we can have this measure differential equation that encompasses the dynamic equation time scales, but we do not know about the other way around. So that's an open question, but we cannot prove even on a counterexample that it's not possible to have this bridge, and we cannot prove that it's possible to have this bridge. So it's something that to think about this type of problem. I mentioned before about such a type of applications of continuous dependency results. So in this way, we can have many types of results in that direction for continuous dependence. As I mentioned, some applications for averaging principles, and also for investigating such a type of maybe attractors. So many different types of results that we can have from this continuous dependence. Also, something that would be interesting to think, and here I brought this question because I know that there are a lot of people working in partial differential equations, is how maybe to relate this with time scales. There are some people that work with partial dynamic equation time scales, and in that sense, okay, they encompass both cases. So sometimes it's very hard to deal with that, especially because we cannot have, for example, until now, some of Fourier transform for time scales. It's an open questions, and there are a lot of open questions in that direction about PDEs on time scales. But it would be interesting to think if it's possible to prove some classical results in that direction. Other way that would be very interesting to think, and in that direction, I include work with Professor Pedro Ubiria and Professor Claudio Cuevas and Diogo Cecílio in one work, that it was to investigate an elliptic partial differential equations on a specific time scales, that it was 8z, and we investigated the solutions of this partial differential equation problem. And we wanted to know about what happened with this type of problem when we change some variables, some parameters, and what happened with the solution. And what we made, we calculated the solution for these specific time scales, that 8z, and we saw that, and we could do with the computer, we could make some graphs and to see the behavior of the solution. And then we made such 8 goes to 0, and then we proved that the solution for the discrete problem converges to the solution of the continuous problem. And we tried to infer about the behavior of the solution, about the stability, and what happens with such a type of parameters when we change, and we pass from the discrete to the continuous, what happened with the solution. So it was very nice in that direction, and there are a lot of open problems. The only thing here is that in order to be able to do that, we needed to deal with radial solutions in that case, in order to have in time, because we wanted to deal with time and for the discretization and so on. But maybe it's possible to think more about these types of problem, how to use these tools from time scales in order to be able to investigate these types of problems. So there are some ways in that directions. And also, only to mention very quickly, there are other types of integrals, that's P5 integral, for example, that many mathematicians use to investigate such a type of partial differential equations with much more general conditions, like not like asking highly oscillating functions, and also much more complications about the functions, about the behavior of the functions in such a type of boundary value problems. So there are lots of problems in that directions that could be attacked using more general type of integrals. So maybe it would be interesting, and also to see such a type of applications that could motivate to have this type of behavior of the functions that deal in this type of partial differential equations. So these are some open questions in that directions, especially about time scales, but of course there are many other things that think in this area, because it's a very new area. So here are some classical questions, especially I brought something about partial differential equations, since I know that there are a lot of people here from the audience working in this subject. So that's it that I'd like to talk today. So thank you very much for your attention.